Welcome back to the Deep Dive. Today we're diving into a question that, honestly, it sounds like something out of science fiction. It's one of those paradoxes in physics that just seems wrong.
It feels completely counterintuitive. You have a particle, the neutron, that for all intents and purposes is immortal when it's inside an atom.
Right. It can last for billions, maybe trillions of years.
Exactly. But the second you pull it out, the second it becomes free, a clock starts ticking. And it's a very, very short clock.
And that's the core of what we're tackling for you today. How can this particle, this fundamental building block of reality, just give up the ghost in a matter of minutes once it's on its own?
Yeah.
It feels like a total betrayal of its nature.
It does, but the answer is all about location, location, location. Inside the nucleus, it's not that the neutron is naturally stable, it's being protected.
Protected by what?
By the most powerful force in the universe, the strong nuclear force. It basically acts like a cosmic straitjacket, holding the neutron in a state where it simply doesn't have the option to decay.
So it's not that the neutron chooses to be stable, it's that the strong force forces it to be stable.
Precisely. It locks it into a lower energy state. A tiny bit of its mass gets converted into what's called binding energy. It's a deficit that keeps it safe. But once it's free, that protection is gone. The strong force can't reach it.
And it's true, unstable nature comes out.
It takes over immediately.
Okay, so that's our mission for this deep dive. We're going to explore that incredibly short countdown, what the neutron actually turns into, and why. And this is the big one. Why those 14 or 15 minutes are absolutely essential for the entire universe to even exist as we know it.
Right, let's start that clock. Because the first thing to really grasp is just how dramatic the difference is.
Yeah, let's just hammer that point home. Inside the nucleus, it's stable, basically forever.
For any timescale that matters, yes. It's what allows for chemistry, for stars, for other... If neutrons decayed inside atoms, everything would just fall apart. But outside, the timer starts.
And you mentioned it's a very specific timer. What is that number? The critical time we need to be thinking about.
It's a number that physicists have worked incredibly hard to pin down. The average lifespan is right around 880 seconds.
880 seconds. So that's, what, 14 minutes and 40 seconds?
Yep, give or take a second or two. It's astonishingly precise. After that short window, poof, it's gone. Not the particle itself, but its identity.
That number just blows my mind.
Yeah.
It's like there's a little alarm clock built into every free neutron in the universe. Why that number? Why not 5 minutes or an hour?
That number is set by the laws of physics, specifically by the weak nuclear force. That's the force that governs this kind of decay. The 880 seconds is just the statistical average of how long it takes for that weak interaction to happen. It's a fundamental constant of nature.
So when the alarm goes off, what happens? You said it doesn't just dissolve. What's the difference?
Well, dissolving sounds like it just breaks apart into nothing or into energy. That's not it at all. It undergoes a fundamental transformation, a change of identity. It doesn't vanish. It becomes something else.
Okay, let's get into that. The mechanics. What's driving it to change? What is it missing when it's alone?
It's missing stability. But in physics terms, that instability comes from a tiny, tiny amount of excess mass.
Wait, you're saying a free neutron is actually a little bit heavier than what it turns into?
Exactly, just a fraction heavier. The neutron's mass is ever so slightly greater than the combined mass of a proton, an electron, and another little particle called an antineutrino.
And because of Einstein's EPC-Ella, that extra mass is really just trapped energy.
You got it. The universe always wants to find the lowest energy state. And for the neutron, that means shedding that tiny bit of extra mass energy and becoming those other lighter particles. It's a downhill roll, energetically speaking.
And this must be the famous reaction we hear about in physics.
It is. It's one of the most fundamental reactions there is. It's called beta decay.
So walk us through it. The neutron decays. What comes out the other side?
3 things. You get a proton, which has a positive charge. You get an electron with a negative charge. And you get that little ghost of a particle, the electron antineutrino.
Hold on. A neutron is neutral, right? 0 charge.
Correct.
So how do you get a positive proton out of it? Doesn't that violate something?
That's the elegant part. The charge has to balance. So the neutral neutron with a charge of 0 splits into a proton with a charge of +1 and an electron with a charge of -1.
+1 and -1. Okay, so it adds up to 0. The balance is kept.
The balance is always kept, and that electron, it spits out. It's ejected at incredibly high speed.
And what about the antineutrino? It always seems like the forgotten third wheel.
It's easy to forget because it barely interacts with anything, but it's absolutely critical. Without it, the math wouldn't work. It carries away some of the energy and momentum to make sure all the conservation laws are obeyed. It proves the decay isn't random. It's a very
Whoa.
orderly process.
So the neutron basically changes its personality. It trades its neutrality for a positive charge and becomes a proton, all to achieve stability.
Exactly. It finds the lowest energy, most stable state it can. Which actually brings up a great question for you. If a proton is positive, and we all know that positive charges repel each other, why doesn't the proton itself decay? Why is it so stable?
That's a good point. If you cram a bunch of protons into a nucleus, they should be trying to fly apart with incredible force.
And they are. But this is where we come full circle, back to the strong nuclear force. It's so ridiculously powerful over short distances that it just completely overwhelms that electromagnetic repulsion.
So the strong force holds the protons together. But where does the neutron fit back in?
The neutron is the glue. It's ironic, isn't it? The unstable particle is the key to stability. By being in the nucleus, the neutrons add a lot of strong force attraction without adding any of that electric repulsion. They act as spacers, keeping the protons just far enough apart for the strong force to win.
Wow. So the neutron needs the nucleus to be stable, but the nucleus needs the neutron to be stable.
It's a perfect symbiotic relationship, and that electron that gets shot out during the decay, that's radiation, isn't it?
That is beta radiation. The instability of the free neutron is, quite literally, one of the main engines of natural radioactivity in the universe. Okay, let's pull the camera way, way back. We have this 880-second clock. It's dictated by the laws of physics. So what? Why should we, here on Earth, care that a free neutron only lasts for 15 minutes?
This is where it goes from being a cool physics fact to the reason we exist. That 880-second timer is a cosmic tuning knob. If you were to change it even by a little bit, the universe we see today would not exist, period.
Explain that. How does a 15-minute timer prevent the collapse of everything?
It all goes back to the first few minutes after the Big Bang. This period we call Big Bang nucleosynthesis. The universe was this incredibly hot, dense soup of particles, just free protons and free neutrons bouncing around.
So no atoms yet, just the building blocks.
Right. And in that heat, they could actually flip back and forth. But as the universe expanded and cooled, that stopped. And the neutron's natural decay, that 880-second clock, became the only game in town. Their numbers started dropping fast.
So the supply of neutrons was dwindling away.
Exactly. That clock ensured that only a very specific fraction of neutrons were left by the time it was cool enough for them to start sticking to protons to form the first atomic nuclei. Mostly hydrogen and helium.
Okay, so it set a specific ratio of neutrons to protons.
A critical ratio. Now let's play the what-if game. What if the neutron lived longer? Say, for an hour instead of 15 minutes.
More of them would have survived that initial period.
Way more. Which means when nucleosynthesis kicked in, they would have gobbled up almost all the protons, forming tons of helium and other heavier elements right away.
What is so bad about that?
No hydrogen would be left, or very little. And what are stars made of?
Mostly hydrogen. That's their fuel.
Without a universe dominated by hydrogen, the first stars could never have ignited. Without stars, you don't get the fusion that creates carbon, oxygen, iron, everything needed for planets, for life.
Yeah.
The universe would have been a dark, sterile, boring place full of helium.
That's genuinely staggering. So that short lifespan is a cosmic gatekeeper. It made sure there was enough hydrogen left over to build the universe we know.
It's a fine-tuning that is just breathtaking. That 15 minutes literally separates our reality from a completely different and likely empty one. It's the foundation of the whole model.
It makes you realize that so many things we think of as solid and permanent are actually balanced on these razor-thin margins, these little decay clocks ticking away.
It absolutely does. You know, there's a saying that the amount of, well, existential dread you can find in fundamental physics is greater than in any horror movie. You start to see how fragile the whole setup is.
And how much patience it must take to study it.
Oh, absolutely. Patience, a lot of coffee, and a strong heart to deal with the fact that all our stability is built on top of a particle that can't wait to fall apart.
So, to wrap up this deep dive, we've got this neutron paradox. It's immortal when it's protected inside an atom, but the moment it's free, an 880-second countdown begins.
A countdown driven by a tiny excess of mass, governed by the weak force. It transforms the neutron into a proton via beta decay, spitting out the radiation that is a key part of our universe.
And most critically, that 880-second timer isn't random. It was the precise setting needed in the early universe to get the right mix of hydrogen and helium.
Which allowed the first stars to form, which allowed us to eventually be here talking about it.
Which brings us to our final thought for you to chew on. If our entire cosmic structure rests on a reaction that's over in just 15 minutes, what other incredibly fast, seemingly insignificant events are happening all around us right now?
What other fundamental processes are upholding our reality that we just don't notice simply because they're over in a flash?
What else are we missing? Because it only lasts for 15 minutes. We'll be back soon with another deep dive.